Wait, that's it. Okay.
So back
Recording.
EMF,
This is somewhat
your brother
slow
uses
quality.
this equation, which is the same thing. So basically voltage minus your back EMF is
Okay.
equal to IR.
Okay.
Okay? And we know, we know,
What was that?
okay, they only give us the percent draw, how much it draws in, as well as the socket voltage. So we know the socket voltage, which is 125 volts. Okay, this is what we're trying to find. Yeah, and we're not given these. So the thing is, how do we compensate for this? Basically, what your brother did is that at the very beginning, before it was, he likes to say before it was even turned on. Yeah, so at the beginning, before it was turned on, he said something like this. Voltage is equal to I naught R. This is before it's turned on.
Okay.
Oh, no, not before it's on.
Which means initial current.
I'll just write what you wrote.
Oh, at
Spell it right. Beginning have two ends.
Yes.
Okay, at beginning, back here. Back EMF is equal to 0. I think this is an Abramia video probably. So at the beginning, back EMF equals 0. So that means the voltage, because there's no EMF yet, voltage is equal to I O R, I not R. So that means if the voltage in general for the socket is 125 volts equals this I naught R. Okay. So the next thing is that we know that the
He's touching my toes.
so now basically what's going to happen is that we're going to have a change in the current, assuming that resistance stays the same. That's what your brother did. So the relationship your brother did is that the new current I, when it's not at the beginning anymore and there is a back EMF, I is equal to the percent they gave you times the I naught. So in this case, the way he did it was 0.16 I naught. So that if we know that this relationship is that the new current is representative of the how it only uses 16% of the voltage here from the outlet, that means the thing that's changing is the current. You have a new current. Okay. So if we go back to here, if we're trying to find R stays the same. So if we know that the voltage is 125 and we're trying to find this, so minus EMF equals, if R stays the same, but we just redefine I as being that. So 0.16 I naught, basically. Okay, so let's get rid of this 125. Let's use it in terms of variables. So to make it easy, that's how we use it. Okay, so we just know that in general, volts minus this equals that. So what we have here is V, okay? And then we can redefine this again as I not R equals V again. So we could just say 0.16 V equals back EMF minus the V, total V that we got from the problem. And then obviously if you do simple algebra, you'll just get V minus 0. Oh crap, can you open this again? 16 V equals back EMF.
Which
So let's just find the percentage, which would be 0.84, or in my case 0.83, times the voltage,
Mm-hmm.
and that should equal the back EMF.
Mm-hmm. Yeah. So that's how it works. So basically, like, actually, no, that actually makes perfect sense because it says when the motor's on, it only uses 16% of the current that is present. So the thing is that, okay, that's why
I get it now.
the brother said, like, okay, if the voltage is 125 straight from the outlet, the current in general will be current times the resistance. We don't know,
Mhm.
we don't care. But it's corresponds to this.
Yeah.
So if the current that the motor uses is 16% of the total current that's going through from the 125, you could just see that the back EMF is associated with the total voltage minus that proportion of the voltage that it's actually using.
Okay.
So the back EMF is equal to the difference. So it's yeah. So the proportion of the voltage that the motor is using, you subtract that from the total voltage from the outlet. The back EMF is equivalent to that difference. That's basically what it's saying. It actually goes to show you that current and voltage are, if you don't know, if R stays the same, current and voltage are directly related.
Okay.
So if you're using 0.16 of the current, you're using 0.16 of the voltage. I don't know if you're using 0.16, but you use 0.16 voltage
Okay.
in the equation. And you subtract the two to get that.
And in this scenario, back EMF represents what?
In this case, back EMF represents the amount of the difference between the total voltage from the outlet minus the proportion of the voltage it actually uses.
So basically, what is not being used?
Yes, I think so. I mean, that would make mathematically.
Yeah,
that makes
mathematically
sense.
makes sense. Conceptually, I mean, it says back EMF does the motor generate. So are we saying the motor is generating a difference in voltage used?
You may have to look at Brahmi's videos for
Yeah,
that.
probably.
But he explains the concept. But mathematically, it's basically the amount of voltage that it doesn't use. Or at least it seems like that.
Okay.
Alright, how do I end? Is it this
Yeah,
one?
maybe.